All right. So, hello again, everybody. My name is Engin Kayraklioglu. I'm the GPU lead of the Chapel team at HP. And in this session, this teaching meetup session, we are going to talk about how GPU support is implemented in Chapel. So in my notes, and I can share these with you, I have this link to the YouTube video for a similar demo session that I hosted in the past, which is more about how to program GPUs in Chapel. Um, so if you're interested in that, check that out, please. Today's session will not be too much about how to write code to program GPUs in Chapel, but more about how things are implemented under the hood. So with that out of the way, I nonetheless have a brief code that I like to show to basically set the tone here and to recap some very fundamental parts of GPU support in Chapel. And it is this code. So what am I doing in this code? So what we have here is a very simple code where we have an array that is on GPU, and we set each element of this array to 2 using this for each loop, and then copy that array into CPU memory. And there's some debugging functions here that I will talk about as well. So this is kind of the basic structure of this code here. If you look at it, there's probably only one thing besides the diagnostics here that is about GPUs, and it is this line. So what happens here is Chapel GPU support revolves around this idea of locales in Chapel, and each locale has GPU sublocale or GPU sublocales depending on number of GPUs that it has. And you can use on statements to move execution or start tasks that are on different locales. This could be like a different compute node, or this could be just a GPU. And here we are starting a new task that is going to execute on the GPU. And what does that mean exactly? So that means any dynamic allocation that you will make, such as array data, will be made on the GPU memory. And any data parallel operation, such as this for each loop, or potentially a for all loop, which is probably more common, will execute on the GPU as a kernel. So these are just a array declaration syntax. This is just a data parallel operation syntax in Chapel. There's no new sort of language tools, if you will, to execute anything on the GPU. It's just you have to run on the GPU, and that's the only requirement that there is. So I'm going to compile this on the right-hand side. And while doing that, I'll also call out this GPU diagnostics module. You don't have to use this. This is, as the name suggested, just for diagnostics. And what I have here from that module is the start verbose GPU and stop verbose GPU. So what will happen when I execute this code is anything that happens between the start and stop calls that involves GPU operations, such as kernel launch and data copy, will be just printed out on the screen. And when I run this code, what happens is, first of all, I see all twos, which is great. And these all twos are actually coming from the CPU array. And on top of that, you are seeing 3 lines of output. So let's just unpack those. So line 9 has a kernel launch, which could be a little bit surprising, but the GPU runtime reports a kernel launch. Why do we have a kernel launch in line 9? That's because Chapel default initializes its scalar types and pretty much everything unless you ask otherwise. So here we are defining an array of integers, and this array of integers has to be set to 0 by that rule of Chapel. So what happens is when you declare this array, it will be allocated on the GPU, and then there will be literally a kernel launch to set everything to 0. So that kernel launch is about that. And then we have another kernel launch in line 11, this one. And that is coming from this loop, which is what we expected, right? So this loop turned into a kernel. And how that happened, how that launch happened, is going to be the discussion of today. And finally, you see from line 15 a copy from device to host that is 80 bytes. And line 15 is this. And we copied 80 bytes from device to host, which is exactly what we expected, because this is an array of 10 integers, and integer is an 8 byte by default. So we copied 8 bytes to host. So that's my quick recap here. We will cover some of the details of how this happened in today's session, and it will be mostly a breadth first, discussion, because it's really impossible to cover anything in detail in 30 minutes or 40 minutes. But I'll try to give an idea of where things are and how things are structured. Before I go do that, is there any questions regarding the recap or anything else?
So how things other than for all loops and array assignment and array declaration get compiled for GPUs?
Sorry, what's the question?
So anything other than for all loops and
Mhm.
array declaration and array assignment. So how are they executed?
So if you have, for example, write ln here, which is an IO function,
Sure.
even though this is inside an on statement that is on GPU, it will be executed on the CPU. So only array allocations and only data parallel operations. And data parallel operations range for each, you can just say, I'm going to delete this. You can just say R equals 2 as well. And this will be also a kernel. This will be also a data parallel operation. But if you call a function, that function call will be just executed on the CPU. For
Okay.
example, let me show something like this. If I have proc foo, and if I were to call foo here, so the call to foo will happen on the CPU. If, on the other end, foo had a for each loop, then this for each loop will also be a kernel. So it's very like a dynamic decision making, if you will. If at that point my task is executing on a GPU sublocale, data parallel operations and dynamic memory allocations will be on the GPU. And that's it. Did I answer your question?
Yes, yes.
Okay, perfect. Any other questions? Okay. So with that, I have, sort of a couple of steps to cover here, and I can probably just zoom into things. All right. So for most anything in Chapel, when we talk about how things are implemented, we talk about internal modules, runtime, and the compilers, and the compiler as a different components here. And the same story applies for GPU support. So we have a lot of code that is sitting in internal modules, and these internal modules are just Chapel code, but they are probably a little bit more. Sorry. Okay, I'm trying to get the screen that I want. They're probably a little bit more on the, low level kind of calling to external functions side of things. It's not typical Chapel code that you would see. And I will start from that because it's probably more familiar. And the first question that is kind of overarching is how do we determine whether something will execute on the GPU or the CPU? And for that, I will just point out, I don't know where to put this screen. Hold on 1 second. Sorry about that. Okay. Um, and for that, I will start with locale model implementation. So if you use Chapel's GPU support so far, what you would probably know is to set Chapel up for GPU support is you have to set an environment variable, Chapel locale model equals GPU. So Chapel has two locale models, flat and GPU. Flat is just standard without GPUs, and GPUs is for GPUs. And this locale model implementation handles a bunch of things, including some details of on statements, and more crucially for us here, how memory is allocated. So this code, this file that I just opened, is where the GPU locale model is implemented. And I will just point out memory functions here, and from there we will just go a little bit depth first. But what we have is, for example, this function called chapel here alloc. So this is one of the fundamental memory allocator functions that we have. And this one is actually typically used for class instances. I will cover memory for array allocations in a minute, but class instance allocation is a little bit more simple for starters. Um, so if you look at this function, what it has under the hood is if I'm running on a GPU sublocale, which is pretty much the general idea, then I will call this function called chapel GPU memaloc. And otherwise, I will call chapel memalock. So these two functions are implemented in the runtime, and I will show the GPU part of it in today's session. But what I want to focus on here is this running on GPU sublocale idea. And I'm checking my notes to see if I'm going ahead. No, okay, I'm not. Okay, um, so running on GPU sublocale is just a helper function implemented here. This is the function that is still in the same module. And what it does is it will call this chapel task get requested sublock. So this function is actually a runtime function. This is not implemented in the modules, and this is the main kind of overarching theme of internal modules, if you will. Like at some point, they will either call a runtime function or a compiler primitive. So this is the case where we are calling a runtime function. And this function is actually, well, where this function is, it doesn't matter that much. It's just uh, checking a struct field. But the idea here is Chapel uses Q-threads for tasking layers, for its tasking layer. What that means is when you're running on 10 cores, let's say, we typically launch 10 p-threads on each of these cores, and then each p-thread essentially has a queue of Q-threads. And Q-threads are user-level threading, much easier to context switch and much lighter weight for us. So that's why we are using Q-threads. And what happens with Q-threads is whenever you create a new Q-thread, or from Chapel user's perspective, a new Chapel task, it gets associated as sublocale with it. So if you go back and remember my example here, where I had an on statement, this on statement actually, colloquially when we say this moves the execution, it actually doesn't move the execution, but it creates a new task on this target locale. And where does that end up going in the code is this file that I have in my notes so that I can avoid grabbing. It's right here. So this is the runtime function that has nothing to do with GPUs particularly. And this is the function that is called when you add a task to a core's queue, if you will. So when you do an on statement, eventually this function is called. And this function has this sublocale ID argument, if you will. And that sublocale ID argument is fed into this thing that we call task bundle. And it goes to this field called requested sublocale. So that's how each task, each chapel task knows which sublocale it's executing on, or which locale for that matter. So that information is crucial for us on GPU support. It's not something that we added or that like there's not too much implementation there that is specific to GPU. It's just something that we are relying on building the GPU support. So this field that we are setting right here is actually what we are checking here. And this chapel task get requested sublock is kind of everywhere. It's what we use for kernel launches, it's what we use for memory allocation. So it's kind of crucial to understand the dynamic nature of decision making here. Any questions so far? All right. So what's next is details of some of the memory allocations. So we discussed chapel hero lock, and this is the function that I showed for that. And again, these are for class instances, which are also dynamically allocated. I'll talk about array allocation in a minute. So here we are deciding between two runtime functions, chapel memalock or chapel GPU memalock. And what we are concerned about here is obviously chapel GPU memalock. And this is where we start looking into runtime. So our runtime has two separate interfaces. One is a more internal one, and I will talk about that next. But the first one that I will talk about is the main interface that this module, the compiler, and some other modules supporting GPU supports interfaces with. And it is in runtime include chapel-gpu.h. So you can consider this as the main runtime interface for Chapel's GPU support. You can see a bunch of functions, including Chapel GPU memalock highlighted here. So these are all the capabilities that Chapel runtime has that it can offer to the compiler and its modules. And chapel GPU memlock is one of them. So let's take a look at its implementation. And the implementation is in runtime src chapel-gpu.c. And chapel GPU memlock is right here. So if you look at the implementation, we have some debugging output here. Um, and what we do here is, again, using the requested sublog of a task to pick the device that we are using. So um, if you attended the runtime, similar runtime session, maybe a couple of weeks back, John must have mentioned that our runtime is basically, so you can imagine our runtime being a process per node. So it's just running per node basis, but it doesn't have information, or it's not specific to any sublocale, or it's not specific to any core. So when you're running our runtime, you have to pick the correct device to execute the functions on, because you might have multiple devices. So that's why for most of our functions here, we have to use this use device function to pick up the correct device. And if you go further in the implementation, you can see this memhook functions. These are not GPU specific. These are mostly about our memory tracking and memory diagnostics module support. So you can check for memory leaks, GPU memory allocation, and stuff like that. There's nothing too specific in these functions that is related to GPU support, and you can see them in our non-GPU memory allocators as well. So I'm just gonna not go into these. And the core of this function is here actually. So what it does is just calls chapel GPU impl memlock. So this is a good point to talk about the second interface that I referred to. So this function that we are looking at is called chapel GPU memlock, and this one is called chapel GPU memlock, GPU impl memlock. So if you are seeing the prefix chapel GPU only, that's the main runtime interface. If you are seeing chapel GPU impl memlock, that's where we are um, trying to cover multiple vendors. So you haven't seen any CUDA memlock or HIP memlock or anything like that here, and that's where chapel GPU impl memlock comes in. So let me show you that interface first. In fact, I can maybe show that on this side, which is in chapel runtime include chapel GPU impl.h. And let me go back to this main header. So on the left-hand side, you are seeing the impl interface, if you will. So you can think of this as sort of the vendor API has to have these implementations, these functions implemented so that the chapel can use that vendor's GPUs. We have support for NVIDIA and AMD, and this header is implemented in two different ways, both for NVIDIA and AMD. And the function that we were looking at before was chapel GPU impl memlock, and you can see it here in this header. And there is an NVIDIA version of this and an AMD version of this, as you might imagine. So let's take a look at the NVIDIA version. And currently I'm running on a system with an NVIDIA GPU, so that's more relevant. And our runtime is structured in such a way that runtime SRC is the main source files, but then there's subdirectories there for GPU layer, task layer, communication layer, and stuff like that. So under SRC, we have a GPU directory, and in that we have NVIDIA and then GPU-NVIDIA.c. So this is where the NVIDIA layer is implemented. And if you search for chapel GPU impl memlock, you can see actual CUDA functions being called. And these CUDA functions, if you are just using CUDA runtime API in your applications, may be a little unfamiliar, but this is called CUDA driver API that starts CUDA driver API that starts with Q instead of CUDA. And this is a relatively low-level API. It's still very similar to actually runtime API, but we are using this low-level API to have more control over things. And the main memory allocation that we are doing here is basically in this if-def branch, and I can talk about this if there's interest, but by default, we are just executing this. And this is a class instance allocation again. And what happens here is this allocates memory that is pinned on host. So class instances are pinned allocations on host that is accessible by the device. So this makes class initialization and class member access much faster on the host that enables a bunch of other things. Well, that makes class initialization much easier, essentially. Is there any questions so far? Are there any questions so far?
So how does the memory block allocated by commemorate host and end up with being accessible from the GPU.
In memory on the host is accessible by devices on CUDA. So we don't do much to support that. It's just was just what CUDA supports.
Okay, so in the CUDA level, you can I presume this is allocating memory on the host, right?
Yes,
But is it still accessible from the GPU?
yes.
Okay,
CUDA will handle the data transfer.
okay,
So typically what happens is like, for example, when you have a chapel array, it's implemented as a chapel record that has a chapel class that points to the actual memory. So this class that is in between is basically on the host and on pinned memory. So the fields of that class, basically members of that class, if you will, can be accessed from the device. And we try our best to not make that happen, but it can happen sometimes where device has to access host memory through this pinned allocation.
yeah,
Because otherwise, when you initialize the class or when you allocate memory for the class, if it's on the device, how are you going to initialize it on the device? I mean, you can make it initialize on the device, but it's a pretty sequential operation. You would have to use a single core on the GPU to initialize the class instance, which feels kind of bizarre for a GPU, right? And there's also another option where you can allocate it on the host, initialize on the host, and then offload to the device. We do that for some very specific things, which I'm not planning to talk about, but I can if there's interest. But we don't do that for any class instance. Are there any questions? So how are we doing on time? Okay, I'm way behind. All right. So let me briefly talk about array memory allocations, which are a little bit different. So I wanted to basically put that in your radar if you're going to do some, GPU kind of research or want to take a, look under the hood. They're a little bit roundabout in Chapel, for good reasons, I think, but it may be harder to find how array data is allocated. So in Chapel, we have this thing called D-data. So you can think of D-data as just C pointers, but having a different type than C pointers allows compiler to do additional things on D-data. And D-data is essentially the array buffer. Any array buffer that you have will be of D-data type. And you can find bunch of details of the D-data type in modules internal Chapel base. So I'm going back to the internal module level again, which is a little bit more higher level. And among other things that you can find here is a function called ddata allocate noinit. So this is the function that allocates buffers for ddata type. And again, this is just array data. And noinit in the name suggests that this just allocates data without setting it up, actually, without initializing it. And what this ends up doing is, again, similar pattern from before. It just has an extern function to chapel memory alloc, extern definition or declaration rather. And this is a runtime function. And this runtime function sits in this header as a static function. You can find it here. And what it does is among bunch of other things, it has some preprocessor magic to check whether we have GPU locale enabled. And if so, we have this function that we are calling if you are running on a GPU locale. This is again the same pattern. It's just a different function. If you go under the hood, it's just checking the requested sublocale of the task that you're running on. And then all it does is it will just call chapel GPU mem array alloc this time. And just to repeat the same things, just so that just for practice, if you look for this function, it's implemented in runtime src chapel gpu.c. And if you look at its implementation, it will just use device again based on the requested sublock, and it will end up calling chapel gpu impl version of it. This is again the same pattern as we observed before. And going to the NVIDIA implementation, chapel gpu impl mem array alloc is implemented here. And again, the default branch is this one. And this time we are just calling cumemalloc. So this is proper device memory allocation. So any array data that you allocate will be just cumemallocked. Or if you're familiar with the driver API, this is identical to cudamemalloc. So that's how array memory allocation works. It's a little bit different code path than the one that I shown before, because arrays are mostly implemented in the module code in Chapel, so array data allocation has to come from module code rather than a compiler injected allocation as the ones that we've looked into before. So that's the array data allocation side of the story. Any questions on this one? All right. So if not, the next step is kernel generation and kernel launch. And this is where we will see some compiler code and where things are arguably a little bit more complicated than what we've covered so far. In this notes, I also have a link to this slide deck. This is kind of an older presentation from 2022, kind of 3 years old. But this is mainly about how the compiler generates kernels in a kind of detailed description. I recommend checking this out. I will not talk about things in this much detail, but I will just show code. I just looked at it yesterday. The ideas that are discussed here and the logic that are discussed here still holds. You will see some differences in interface. That's the kind of natural evolution of things. But if you're interested in compiler implementation, I would recommend checking this out offline. All right, now let's go back to where we were. Let's go back to our code again. And I have this. OK, so what I will do next is I will compile the same code, or maybe I can just use the precompiled one. OK, let me take a step back. So I have this line here that you can use to compile your code while generating the internal, while generating or dumping the LLVM IR that we generate from it. So for GPU support, you have to use the LLVM backend, and using LLVM backend means Chapel compiler emits LLVM IR, and you can inspect that LLVM IR to see how kernels are launched and things like that. You can use something similar but a little bit more advanced to inspect the generated kernels. I can talk about that as well, but it's not on my agenda so far. I can definitely do that after we are done. So I already did this yesterday, so let me show you the generated LLVM IR. Okay, I'm going to go full screen here to avoid line wraps. So I'm going to show you the kernel launch site here. Okay. So this is a kernel launch site in the generated LLVMIR. So this code is just executing on the host. There's nothing about GPU here. It's just the entry point for a GPU kernel. So the core of it, as you can see, probably is Chapel GPU launch kernel. And this is a runtime function that I will cover. And this is all generated by the compiler. And if you look at this whole block, what it does is it will initialize a kernel configuration. So this is again a runtime function, and a kernel configuration is a rather big struct in the runtime, which I will cover again. So to initialize the kernel configuration, this will involve like passing the kernel name so that the driver API can find the kernel, number of arguments that I'm going to pass, block size, number of threads, and stuff like that, like this kind of fundamental configuration of the kernel. And then you'll see a bunch of calls that are Chapel GPU arg pass. There could be other functions that are called about arguments if there are more complicated arguments. This is a rather simple example, so you can see 5 Chapel GPU arg pass calls. So this kernel has 5 arguments, and we are passing each one of them through this Chapel GPU arg pass. And by pass, I mean we basically keep configuring this kernel configuration type that I will talk about in a minute. And once it's completely configured, we just call Chapel GPU launch kernel with that configuration. And then at the end, we just d'init the kernel configuration. So this is all the code that compiler generates for kernel launch. It also generates the kernel, obviously. And then the actual launch and details of the launch are implemented in the runtime. Before I go look at the runtime side of things, I will also take a step back kind of from this point and talk about a little bit what's happening before this part. So because remember, everything is decided dynamically. So we always check whether we are executing on a GPU sublocale or not. So a loop can execute as a loop if it's not executing on a GPU sublocale. And if you go up just a little bit, you can see a call to the function is a little bit mangled, but this is the function that we are familiar with so far, I'm hoping. So this is the function from the runtime that gives you the requested sublocale of a task. So what's happening here is we are just asking for that, and if we are executing on it, we execute this branch through this branch, and if not, we go to 461, which is here, which goes to 462, 463. This is pre-optimization, so this will all go away. And it will just fall back to this, and which will end up being a loop. So again, in the generated LLVM IR, you can see that we are still making that dynamic decision. Any questions on the LLVM IR side of things? Otherwise, I will start talking about these runtime functions here at a high level. Okay, so we are vendor neutral as much as we like, as much as we can. And so these kernel config initialization and kernel launch and everything like that are completely vendor neutral implementation in Chapel. So they are in the top level of runtime. So that's runtime src chapel gpu.c. And for example, the first function that we were covering here, chapel gpu init kernel config, oh, there's more than one kernels. It's actually right here. It's implemented here. It's in the same header that I was showing before. And it basically revolves around this kernel config type, kernel underscore config. And if you search for it here, it's basically a type in this implementation in this source code, in the source file. And this is kind of the core of kernels in runtime. And I believe there's plenty of optimization or at least investigation opportunities here that we haven't explored so far. So this kernel configuration is a rather big struct that is gradually constructed through this function calls like chapel GPU argpass. So if you find chapel GPU argpass, it ends up calling this CFG add direct param. If you find that function, it's actually, we call this a lot in a bunch of other places too. So what it does is essentially records some information about the argument and just bumps up a counter so that the next argument can be put in the correct place. So this happens 5 times here, for example. We populate some fields in the CFG, which is the kernel configuration struct again. And then we end up calling chapel GPU launch kernel. So this is the main function where we call the kernel. It's a little bit underwhelming when you think about, this is the kernel launch. There has to be a bunch of stuff happening here. There is something happening in launch kernel function, which I will talk about, but the key idea here is bunch of the complicated stuff that needs to happen for kernel launch to happen is actually happening before through this kernel configuration type. And this kind of a core information, in my view, in understanding how runtime works when it comes to kernel launches. So it's building this kernel configuration type gradually in a way that you can launch the kernel is kind of important here. But let's look at the launch kernel function nonetheless. This is rather boring implementation here. It's pretty much standard checks, debug calls, and stuff like that. And then if you go to the launch kernel, it's a little bit more complicated and it's more fun to look at. So we are using the device, bunch of diagnostics happening here. And here we are calling an impl function to actually get the function that is the kernel that is generated by the compiler. So both HIP and CUDA works by name-based lookups. So we literally pass the kernel name that we generate, and then it can go and find the function. I can show you this function, but it's rather simple, really. And then going forward, bunch of other debugging stuff. So if you come to the core of it, which is here-ish, I will not talk about this, but I can offline after the call. But this is about our initial support for distributed arrays in Chapel at a high level. And this is about our initial support again for halting from GPUs, which we currently do not support. But is both of them are kind of work in progress. You can't see the impact of them on user code just now, but things are coming up there. And then the core of it is just Chapel GPU Impl launch kernel. Just to show you my point that this is boring, I'll just show you how it's implemented for the NVIDIA version. It's just 5 lines of code. Oh, sorry, this load function. Sorry, it's maybe even shorter. Yeah, it's even shorter. So it's essentially making sure that we get a kernel just for debugging purposes, and we end up calling co-launch kernel. So this is again something different in the driver API that we are using. So there is no like angle bracket syntax that you might be familiar with from CUDA. It's a lower level way of launching kernels, and we like that because we can pass bunch of configuration things to it. And when that kernel launch happens, we have another call for reductions if there's any. Okay, sorry. We have another call for halting again. This is work in progress. We support reductions in kernels. We have to do some follow-up if there is any reductions happening in the kernel. And then what happens is kind of another important point here, is that um, by default, uh, GPU operations are executing on a GPU stream. That means they are asynchronous. So far we haven't really synchronized anything on the device. So we launched the kernel, we put bunch of other stuff into the same stream, but the kernel might still be executing as the host is doing all this stuff. And ignore this if def. It's not. It's for profiling purposes, obviously. Um, so what we do next is we let the current host task that launched the kernel to yield. So this is a way for us to enable host and device overlap communication, or like host and device overlap essentially, because otherwise the task will keep running. There's nothing asking in the runtime to make the task yield from once it launches the kernel. So this allows a lot of the overlap stuff that we enable. And then a bunch of stuff is also added to the same stream. So this is going to the, again, stream. Well, my note says it's otherwise. It should be going to the stream, and it's another potential work area. And at the end, we just wait for the stream. And if you look at this implementation here, this will be, we'll just check the stream. And if it's not ready, we'll just yield the task. And if not, we'll just synchronize the stream and move on. And that's the kernel launch interface in the runtime. I'll stop here again to see if there's any questions. I know I'm going too fast, but I'm trying to cover a wide range of things here. So I'm sure there are questions there. Not. So that was the entry point of our launch kernel. Let me go back and check my notes. Where am I? Did I cover everything that I wanted to do? Okay, so one of the I referred to some potential optimization opportunities. Since this is about the implementation details, I will talk about it. So as I mentioned, we gradually built this kernel configuration struct. And if you look at the generated IR, we initialize it, launch the kernel, and then we deinitialize it. So what I would like to show you is the deinitialization part. So what we do here is, and I'm not going to talk about the details too much. It's actually a bit too much boilerplate. We essentially free bunch of memory that we allocated during initialization. So we allocate these memory gradually during initialization, and when we deinitialize, we deallocate it. But in many applications, you repeatedly call the same kernel, maybe with slightly different variables, but you pass the same number of arguments. Bunch of things remain the same, actually. So an interesting idea here to pursue is whether we can cache some of these kernel configurations. We create it, we discard it really easily. Keeping them alive for a while, if a kernel is being launched repeatedly, could save a lot of time in kernel configuration, initialization, and deinitialization. Now, that being said, I do not know if a practical use case that is out there, or like a benchmark or a mini app or something like that, where we suffer from this significantly, but there could be some. Like I can see that we are wasting a lot of time initializing and deinitializing same things again and again and again here. So I wanted to just put that as an idea, as a potential researchy work area that could be beneficial in production too. That's something that I had in my notes. With that, what's next is very brief overview of the compiler. Because understanding the compiler implementation, it's a little bit like you have to understand the full compiler and the full structure to dig deep into it. So that's why I kind of emphasize runtime a little bit more because it's C code. There's not much too specific about Chapel there. On compiler side, things are a little bit different. So, but let's begin nonetheless in the last couple of minutes that we have. So the core thing in the compiler is this GPU transforms pass. It's not literally a pass, but you can see it as a pass. And this is 2,500 lines of code, not too modest, not too large either. And this is where we essentially generate this IR that I was showing. This is not generating IR, to be clear. This is just generating more internal representation in Chapel's abstract syntax tree. But it will turn out to be this IR generated a couple passes later. So what it does is it will just generate this part of the code, and it will also generate the kernel itself. And the core function that I wanted to show here was, I believe, okay, generate kernel launch. So this is the part where we generate the block that I keep showing in the generated IR. And let me show you side by side here. Okay, so we discussed Chapel GPU init kernel, for example, that is here. And it's essentially added through this primitive. So Chapel compiler has what we call primitives. You can think of it as like intrinsics in other compilers. So this is just a compiler primitive that we add. You can think of it as just a call. And it will literally turn into this call during code generation phase. And into this kernel configuration initialization primitive, we add bunch of arguments. And these arguments are the arguments that you can see here in this call. And then what we do next is adding what we call PIDs. And this is again for distributed array support. And it's not completely done yet, so I'm just gonna glean over it. The next is adding actuals. And in fact, let's do this breadth first. So we populate this kernel actuals argument. Okay, I take a step back. I'm not gonna do that depth first. I'm gonna keep going breadth first. So somewhere we created these actuals, and I will cover those as well. And for each of these actuals, we do this, we call generate prim GPU arg. And if you look at this implementation, it's another primitive expression added, and this is GPU arg primitive. And oops, what happened? Where am I? Okay, sorry about that. It's another GPU arg primitive, and it turns out being these Chapel GPU arg pass functions during code gen phase. And then we generate the kernel launch, and then we generate kernel deinitialization. So this is where this block is generated, generate kernel launch. I talked about actuals, and that brings me to my last point that I wanted to make in the compiler, and this is a function called populate body. So populate body is a function that populates the kernel body. So what it does is it will iterate over the loop body, and it will gradually build a kernel body. I think it's a nice implementation, but it's one of the things that if I had time to refactor the compiler, GPU part of the compiler, I would probably refactor this a little bit to make it more maintainable. But it's not to say that it's like spaghetti code or anything like that. So this will just iterate the loop body, check bunch of things. If it's this kind of an expression, do this. If it's that kind of an expression, do that. One of the things that you will see here is this add user var kernel argument. So this is basically how kernel arguments are added for a kernel. And if you look at its implementation, it will go to add kernel argument helper. And what did I want to show here? Oh yeah, so what it will do is it will end up adding things to this kernel actuals um, vector in C++. And this kernel actuals vector is where we actually did the generate, so this function visited. So this is actually where we are iterating that vector that we populate over here to generate the kernel arguments. And this again ends up being Chapel GPU argpath. Okay, that brings to my very last point, which is the codegen side of things. So we have these bunch of primitives, but how do we actually generate the IR associated with that? Just to point out where they are, if you go to compiler, codegen cg-expr, so this is where expressions are code generated, and this is a rather large file, as you can see. But you can search for things like GPU arg. So this is a primitive definition in this code, and you can see a bunch of other GPU primitives here in the same place as well. So this is where we do the Chapel GPU argpath generation, and we do a bunch of type checking um, for the argument, and there are many different ways of passing an argument. And here, this is probably one of the more complicated code jump functions for GPU. Depending on what kind of argument we passed, we generate calls to Chapel GPU arg offload, Chapel GPU arg reduce, Chapel GPU arg host register. These are all different kinds of argument passing strategies that I haven't covered. But the most basic and most common one is Chapel GPU arg pass, which is what we are seeing here. And this is where that code generation happens. And this is we end up calling this function codegen callexpr with args, and this is a very standard codegen function that has nothing to do with specifically about GPUs. That's, I think I covered everything that I wanted to cover. There was a lot and a lot of nitty gritty here, a lot of nuts and bolts. Um, any questions? Well, first of all, thanks for sticking around. Then thanks for interest. I'm sure there are a lot of questions, but any questions that we should discuss right now? And with that, I will stop recording. Thanks again.